All right, so I'm going to start off by showing you an example of how to find your least square regression line in your calculator. And so I'm going back to the example that we used from section 3.1 about the candy and the calories. And so here I've entered the X values, which was the sugar, and then the Y values, which is the calories. And so if you recall, when I do menu 4, 1 stat calculations, and remember, you're going to select linear regression where it says A plus BX. And so I have my X list, which was sugar, my Y list, which was calories. The rest of them, it doesn't matter. Hit enter. And so you can see here, whenever I create this linear regression, it gives me my A and my B value. Remember, your A is going to be your y-intercept, and then your B value is going to be your slope. You are also given these other values of your R, which is your correlation coefficient, and then we're going to eventually talk about R squared, which we're going to see in a second. Now, if you recall, to graph this, I'm going to do Control Doc, going to go for data and statistics. And then on the x-axis, I'm going to put sugar. Then on the y-axis, I'm going to select calories. So this should match what we did in the first section. And so then from here, if I want to see the least square regression line on here, I'm going to press menu. I believe it's 4. Then you can go to 6 for regression and show linear. Okay. So then you can see there that I have now the least square regression line on this graph. Now, you have to do this first if you ever plan to look at the residual plot. To view the residual plot, that was in our notes that we did yesterday, we have from your residual plot or scatter plot, you're going to do menu, you're going to go to 4 for analyze. And now that we've done the regression, you should be able to view your residuals, and you're going to select 2 for show residual plot. And so you can see here, it's going to do kind of a split screen. You have your scatter plot above, and then you have the residual plot down below. Okay. So remember, this line at 0 is basically your least square regression line turned on its side. And then each distance from that line shows your residual. So you can see that this one has a residual above the least square regression line. These have it below. Now, you once again, remember to use this residual plot to determine is a linear model appropriate. It is considered appropriate if it is evenly distributed above and below the regression line and that there is no curved pattern. Because if there is a curved pattern, then you would consider nonlinear, which we can't have a linear regression for something that's nonlinear. Now, continuing, how well the line fits the data, the role of S and R squared in regression. So the standard deviation of the residuals S, okay, measures the size of a typical residual. That is, S measures the typical distance between the actual Y values and the predicted Y values. So similar to before, how I've talked about interpreting is super important. This is something that you need to reference. It says the actual Y variable is typically about S standard deviations away from the predicted Y variable by the least square regression line with X equal to X variable. So you're going to plug in your BSing into each of those that we, similar to how we did for slope and Y-intercept. Okay, so once again, your S is the typical distance of a residual between the actual and the predicted. Now, the coefficient determination R squared. Okay, this can be either given to you, or if you know your R, well, you can square it to find R squared. This measures the percent reduction in the sum of the squared residuals when using the least square regression line to make predictions rather than the mean value of Y. Now, that probably makes no sense, okay? In other words, R squared measures the percent of variability in the response variable that is accounted for by the least square regression line, okay? So it's the percent of variability. Now, once again, most of the time, all you're going to be dealing with R squared is to interpret it. So here is the template that you would use for interpreting the R squared. So it says about R squared percent of the variation in the Y variable is accounted for by the linear relationship with X. Okay. Keyword in here being variation. Okay. So let's do some examples of this. In the example about the candy grab, it says for this data, technology gives you that R squared is 0.697 and S equals 4.03. We are going to interpret each of these values. So if that's the case, let's start off with our R squared. Okay, so in this case, our R squared is 0.697. This is the same as 69.7%. So we're gonna say about 69.7% of the variation in the number of candies grabbed can be accounted for by a linear relationship with handspan. Or X equals handspan. Okay, so notice once again, all I'm doing is using this template, plugging in my BS for the Y variable, which was number of candies grabbed, and my X variable, which was the hand span in centimeters. Okay, now my S, which is 4.03, starts off with, using this template, the actual number of candies grabbed. So the actual number of candies grabbed, okay, is typically about 4.03 standard deviations away. Okay, so you can go back and look here. Away from the predicted Y variable, from the predicted number of candies grabbed okay, by the least square regression line with X equals to the handspan. So by least square regression line, remember you can use that for short, with X equal to handspan. Okay. So you have the interpretation for an R squared and you have an interpretation for the S. Now, continuing, interpreting the computer regression output. Sometimes you are not going to necessarily even have to use your calculator because they are going to give you what they call a computer regression output, okay? The figure below displays the basic regression output for the Ford F-150 data from two statistical software packages, Minitab and JMP. Other software produces very similar output. Each output records the slope and the y-intercept of the least square regression line. The software also provides information that we do not yet need or understand, although we will use much of it later. Be sure you can locate the slope, the y-intercept, and the values F, S, and R on both computer outputs. So you have two different types here. You have Minitab and JMP, which are the more common ones that you are going to see. But as you can see here in this example, if you recall, the slope for the truck one was 38,257. This was technically my A value in the equation. Okay, and you're going to find this because it says constant. And if you notice, the y-intercept is a constant value, and so it's going to be in that row. The slope, if you recall from the equation, is always next to your x variable. Well, x in this case was our miles driven, and that's going to be, in this case, coefficient for x is negative 0.16292. So that was our b value. All of this stuff over here, you are not going to use, okay? This represents the standard deviation of the residuals. That's our S value. And then you have your R squared, which is 66.4%, okay? Do not use the adjusted R squared, okay? Only focus on the RSQ. Now, if you were to have this one over here, okay, your R squared is this top one. Once again, do not use the adjusted, okay? Your root mean square error, they call that the standard deviation of the residuals. Okay, so this is basically our S. Then you look down here, the other ones don't matter. Then you look down here, okay? Once again, intercept, pretty straightforward. That's your A value, okay? And then miles driven, once again, that's your X variable. And so the estimate for your X is technically your slope, which is B. So let's look at this example here. Using feet to predict height. A random sample of 15 high school students was selected from the U.S. Census at School database. The foot length in centimeters and height in centimeters of each student in the sample were recorded. Least square regression lines were performed on the data. A scatter plot with the least square regression line added, a residual plot, and some computer output from the regression are shown below. So this graph down here is considered our scatter plot. This line is referring to the least squares regression line. This one is what we call our residual plot. And I know this because it says residual on the side. Okay, and this is also our least squares regression line as well. So in this example here, your explanatory variable is considered your foot length, which is our X, and then your height is the response. Okay, so we have this information here, which we're going to use in a second. But if you flip over to the next page, you have also the computer output. Now, when it comes to the computer output, you should be able to determine the equation. So this is the computer output. So let's look at the first question. It says, in A says, what is the equation of the least square regression line that describes the relationship between foot length and height, and define any variables you do? Now, there are two different ways to do this. You can either identify what your X is and what your Y hat is, because remember, you need to know this, separately and then write your equation, or you can write it within the problem, okay? So in this case, X we know is going to be the foot length. And then our Y hat is technically our height. So I could write the equation Y hat equals, now I need to figure out what is my A and my B. Well, I'm going to go to my computer output, and your y-intercept is going to be found where it says constant. And so this value right here is my y-intercept, which is going to be my A value. And then notice the foot length is our X values, and the coefficient of X in this case is 2.7469, which is my B. So we're going to end up with 103.41 plus 2.7469X. So this would be suffice for this answer. However, if you don't do this, you can say the predicted height equals 103.41 plus 2.7469 parentheses foot length. So you either need to have this format where you BS inside the equation, or if you're going to only write this, you better have what X and what Y hat equal out to the side, okay? B says, let's interpret the slope of the regression line in context. So we're going to say for every 1 centimeter increase in my X value, which is foot length, or X variable, there is a predicted 2.7469 centimeter increase in the height. And remember to go back and look at your template for how to interpret the slope of a regression line. Okay, and I knew it was centimeters because if you look back at the problem, the graph is labeled as centimeters for both of those. Now, part C says to find the correlation. Well, when I'm referring to the correlation, that means I basically need to find R. Well, we don't have the data to actually put this in the calculator, but we do have a computer output, which gave us an R squared. So they tell us that R squared equals 0.486 because they gave us the 48.6%. And so I can convert this to a decimal. And if I want to find R from R squared, technically all I need to do is take the square root. And in this case, because when you take the square root of a number, you can have either the positive or the negative of it. If you were to stick this in their calculator, you would get 0.697. However, because of the fact that I need to go back and once you've determined this value, you need to determine, is my slope positive or is my slope negative? Because remember, your R value tells you your direction, if it's a positive or if it's a negative value. Well, my slope was a positive, so that means that my R also needs to be positive. So therefore, R equals 0.697. And then D, it says, is a line an appropriate model to use for this data? Explain how you know. Okay, when you do this, you're going to look at residual plot. Okay, so you're going to use the residual plot. So if I go back over here, because a residual plot is used to determine if a linear model is appropriate. Now, some of the things that you need to remember is that for a linear model to be appropriate, the residual plot needs to be evenly distributed above and below the line, and there needs to be no curve pattern. In this case, the dots are kind of all over the place. So we don't necessarily have any curve pattern, and it's a roughly estimate or same amount on top or above and below this line. And so we can say, yes, a linear model is appropriate. Because there is no obvious pattern and points are evenly distributed, or sorry, no obvious pattern in the residual plot, and the points are evenly distributed above and below the regression line, or above / below the least square regression line. Okay. All right, correlation and regression wisdom. The distinction between explanatory and response variables is important in regression. The least square regression line makes the distance of the data points from the line small only in the y direction. If we reverse the roles of the two variables, we get a different least square regression line. This isn't true for correlation. Switching the x and y does not affect r. Okay. So I'm just going to sum up what this says. If we switch x and y, your A and your B changes in LSRL, but R does not. Okay, that is basically what this first bullet here is saying. Okay, if we switch the x and the y values, your slope and your y-intercept are going to change for the least square regression line. However, your R value is not. Now, your correlation and regression line describes only a linear relationship. Okay, so once again, linear relationships. You can calculate the correlation in the least square regression line for any relationship between two quantitative variables, but the results are useful only if the scatter shows a linear pattern. Always make sure you plot your data if possible. Okay, if they don't give you a graph, but they give you the data, plot it to make sure that it created a linear pattern. So then in this example, the following four scatter plots are very different associations. Which do you think has the highest correlation? Okay, so you can see here we have a supposed linear form. Okay, it's going in the up direction. However, this one clearly, this is non-linear because it created this curve. Okay, this one we can still consider linear, but notice this one we have an outlier. Okay, and so maybe the least square regression line would be about right here. And this, even though all the points are going straight up and we have this outlier here, this one would create a least square regression line about this. All four of these actually have the same correlation of R equals 0.816. So it's very important that you make sure that you look at the scatter plots to make sure that they create that linear form, and also look at the residual plots because sometimes those also can be misleading. Now, correlation and the least square regression lines are not resistant. That means you already know that correlation R is not resistant, so it's going to be impacted by your outliers. One unusual point in a scatter plot can greatly change the value of R. Is the least square regression line resistant? No. Okay, the answer is no. So in other words, outliers change your A, your B, and your R. Okay, because remember, A and B are parts of your least square regression line. Okay, so that's important to know. Outliers are going to affect all of those. Now, you can have points with high leverage in a regression have much larger or much smaller X values than the other points in the data set. You can have an outlier in the regression is the point that does not follow the pattern of the data and has a large residual. Okay. And then you can also have an influential point in a regression is any point that, if removed, substantially changes the slope, the y-intercept, the correlation, coefficient of determination, or the standard deviation. So if you take out a point, sometimes it's going to be considered an influential point if it has a substantial change. So let's look at this example here so you can get some ideas of what we're talking about. So the scatter plot and residual plot for Giselle adaptive scores versus the age at first word data are shown on the next page. The two outliers, child 18 and child 19, are indicated in each plot. Child 19 has a very large residual because the point lies far from the regression line. However, child 18 has a fairly small residual. That's because child 18's point is close to the line. How do these two outliers affect the regression? So let's look at this. Okay, so here is our scatter plot. Okay, you have the least square regression line. This is your least square regression line. So you have child 19, which is not in the overall pattern, but then you have child 18 down here who is close to the pattern, but it's away from the other points. So then you're going to also have that same graph, but now you have the residual plot on this side. So you got child 19. Notice they mentioned how it has a larger residual. Okay, so it has a large residual. And then child 18 has a smaller residual, but it's further away from all these points. Okay, so the figure below, we need to figure out what's considered an outlier versus which is considered influential. Okay, the figure below shows the results of removing each of these points on the correlation and the regression line. The graph adds two more regression lines, one calculated after leaving out child 18, and the other after leaving out child 19. You can see, okay, so this one is technically the original least square regression line. Whoops, sorry. Okay. So this one right here is your original least square regression line. If you were to take out child 18, notice, okay, so with all 19 points, you have a slope of negative 1.127 and a y-intercept of 109.9, okay? That's for the yellow one. If you were to take out child 18, notice, okay, so if I take out this one, how my slope changes quite a bit. It went from negative 1.127 to negative 0.779. It's still negative, however, it is a less steep slope. Okay. And then my y-intercept didn't really change too much because of the fact that it was still kind of in line with it. Now, if I were to take out child 19, notice my slopes on these are about the same. Okay. And so it says removing child 19 has little effect on the regression line. Okay. So just be aware of outliers are considered to have large residuals. So you would consider this to be an outlier. And you would consider this to be influential because it changed our slopes so much versus having that point included versus not having it included, okay? And then lastly, association does not imply causation. We talked about that a little bit in the previous section. When we study the relationships between two variables, we often hope to show that changes in the explanatory variable cause changes in the response variable. A strong association between two variables is not enough to draw conclusions about cause and effect. Sometimes an averved association really does reflect cause and effect. So think about, look back in your 3.1 notes to refer to that, okay? So that's gonna be all the notes for 3.2. You will have Khan Academies about this that I posted in Schoology. If you have questions,